Now we're going to take a look at putting all this stuff into use that we've been talking about, the end behavior, the real zeros, the x-intercepts, and the degree of a polynomial, all this stuff. Okay, so here I have a problem. It says form a polynomial function whose real zeros are -2, 3, and 5, and has degree 3. Okay, so some features of the graph. And what we're going to do is find the function itself. Not the graph, but we're going to find the equation of the function. Okay, so now, as I look at this, I know that if I have a real zero, I can create a factor from that real zero. Okay, so each of these gets their own factor. It's going to be x minus that number. So the first number here is -2, so x minus -2 is my first factor. 3 is the next real zero, so x minus 3 is a factor, and 5 is a real zero, so x minus 5 is a factor. Now I would simplify this and then simply make sure that my degree is 3. Okay, well it's going to be, because when I multiply x times x times x, I get x to the third, which is fine. If this number was, say, a fourth power, or degree 4 or degree 5, I may need to add exponents to these factors to make them work out. Like if this was a degree 4, maybe I throw an x square, or throw a square on this factor, or any of the factors, to make all the powers add up to 4. I just need to make them add up to the right degree. Now, this says form a polynomial. There could be many options, right? This one really is pretty much narrowed down. If I simplify this, it's x plus 2 times x minus 3 times x minus 5. Okay. If this had said degree 4, I may have thrown a square on any of those 3 factors, in which case there are 3 different answers. However, what's interesting is there are actually an infinite number of degree 3 polynomials that have these 3 factors. Or these 3 real zeros, if you think about it. If I were to plot the graph that has factors at, or x-intercepts at -2, 3, and 5, just stick them somewhere on the graph there, then I could have a cubic, can't even say it right. I could have a cubic look something like this. That would go through all of them. I could also have a cubic, this one has a positive leading coefficient. I could also have a cubic that has a negative leading coefficient. And that would also be a valid cubic that goes through the same 3 points. I could even stretch this graph out. I could do some transformation, so I could make a even steeper graph that still has the same 3 x-intercepts. And so I could vary the shape slightly and still have a degree 3 polynomial with these 3 x-intercepts. Now how would I change that? What would I do to my equation to make the graph change like that? Well, I have to add in or account for some sort of leading coefficient. Okay, the leading coefficient is what makes the stretching and reflecting occur when we're doing our transformations. So here I have a general a sub 3, that would be a 3rd degree leading coefficient. That's our notation for it. But it could be anything. It could be 1. 1 would be nice, right? Then I don't really need it in there, and I just write those factors. But if that that could be really anything. And so I'm not specifying. I said form a polynomial. So in that situation, and you're going to see some of these in my math lab, in that situation where it just says form a polynomial, the answers could vary. Generally speaking, we tend to like using just a leading coefficient of 1. Just makes everything else work out a little bit nicer. You don't have to worry about trying to find it. There are actually going to be some problems or some examples where you have to find a specific leading coefficient, and we'll do one of those in the next video.